So, Carolina will start recording. Good morning, everybody. Thank you for being here. This is another seminar from the Instituto de Astrofísica de Andalucía. And today we will have the talk by Dr. Carolina Casadio from the Institute of Astrophysics in Crete, in Greece. And she will talk about search for a milli-lens to discriminate between dark matter models. Carolina, she focused her research career today, and she has been in relativistic jets in active galactic nuclei. And they study in very long baseline interferometry and multi-wavelength polarimetric data. She obtained the PhD here in Granada, in Spain, at our institute, in Instituto de Astrofísica Andalucía in 2016, under the supervision by Dr. José Luis Gómez and Dr. Iván Agudo. And after that, after the PhD, she moved to the VLBI group of the Max Planck Institute in Radio Astronomy in Bonn, in Germany, for her first postdoctoral appointment, where she shifted the attention to millimeter VLBI radio data. Then, at the beginning of 2020, she moved to Crete, in Greece, to join the research group led by Professor Vasiliki Pavlidou and Kostas Stasis at the Institute of Astrophysics there. There, she added one more piece of information to her studies, including the dark matter and the leading group of undergraduate students and PhD researchers for the pilot project of SMILE program that she will be presented today. So thank you very much, Carolina, for being here. And the floor is yours.
Thanks for the presentation. Thanks to invite me here. So hi, everyone. So as you just heard, I'm a radio astronomer, and my background is actually focused on relativistic jet in active galaxies, mostly using very long baseline interferometry. And that's why today I will give you a talk on dark matter models. So yes, it's yeah, I hope you're laughing behind your screen. It's a bit awkward to have this online, but this was partially a joke actually, but partially not, because I will really give you a talk about this recently started project called SMILE that we recently started with some collaborators. Some of them are named here in the presentation. SMILE stands for Search for MIlli-LEnses, and in this project we use the gravitational lensing on the key but poorly explored the milliarcsecond scales to discriminate between dark matter model. And I will show you now how also VLBI and AGN physics have fortunately something to do with this project. So let's start with this nice plot that tells us how few we know about our universe. It is now known that roughly the 95% of the total energy content of the universe is made of unknown forms of matter and energy. And in the standard cosmological model, this matter is in the form of cold dark matter, therefore the LambdaCydia model, where particles are non-relativistic at their origin and they are collisionless. But because of the elusive detection of these of the dark matter particles on one side, and because of the remaining discrepancies between LambdaCydia predictions and observation at some scales, on the other side, then there are still many viable dark matter models on the table of discussion. And actually, some of them have been thought exactly to solve some of the issue of the LambdaCydia model. Here I named just some of them. This doesn't pretend to be a review on dark matter models, so I probably name the most cited in literature. So for example, the self-interacting dark matter model, where particles are still called dark matter particles, but they scatter elastically between each other. Then we have the physical dark matter model, where particles called dark matter particles are ultralight. And then the famous also warm dark matter model, where particles are, for example, semi-relativistic at their origin. But dark matter doesn't have to be necessarily a particle. There are in fact also non-particle candidates, like for example, primordial black holes. These objects, depending on the epoch of formation, they may have very different masses. And actually there was a renewed interest on this object associated to the recent detection of the gravitational wave signal from emerging of two black holes, where the primary black hole has a mass of around 85 solar masses, and this has risen doubts on its stellar origin. So, as I mentioned before, the LambdaCydia model is very successful in predicting the formation of large-scale structure in the universe, but it still has some issues, and mostly at smaller scales. For example, at sub-galactic scales, so we're talking about masses below 10 into 10 solar masses scales. It predicts, for example, a number of dark matter halos that is far above the observed number. And this is what you have in this plot, for example, where you have the curve represent the prediction from the LambdaCydia model, while instead the triangles are the satellite galaxies in our Milky Way and the Andromeda galaxy. But not only the predicted number is different from observation. Also, it seems that they also have different density profiles than what is predicted by LambdaCydia. In this plot, for example, you have the density profiles on a large number of dwarf galaxies from the Little Things survey in O et al. 2015. That are represented by these green points. And as you see, these green points, so in the central region of the dark matter halos, they are rising more slowly than the gray curves that instead represent the prediction from the CDM and Navarro-Franke-White density profiles that predicted the formation of a high density cusp in the central region of dark matter halos, while instead the observation of these dwarf galaxies point more toward the formation of a core-like center. And for this reason, sometimes this problem is addressed as the core cusp problem. And it is at these subgalactic scales where different dark matter models make very different predictions. Indeed, here you have the power spectrum of baryonic acoustic oscillations at different masses and different scales. The gray shade area is highlighting exactly these subgalactic scales, and the blue curves are for different dark matter models. So let's, for example, consider the blue solid line that is the cold dark matter model, and instead the dashed line that is the warm dark matter model. If you see, the warm dark matter model has a cutoff around 10 to the 8 solar masses, while the cold dark matter model stays up. And this is, for example, is telling us that if the warm dark matter model is correct, then we don't expect to observe dark matter halos below a certain mass, below around 10 to the 8 solar masses. So let me say that in general, different dark matter models make very different prediction on the expected number of dark matter halos at subgalactic scales, and as well as about their density profiles. And this leads to the natural conclusion that estimating the number of dark matter subgalactic halos is very important, and it can help discerning the nature of dark matter. So then why nobody has been done this before? Why nobody has been tightening this number? So mostly because dark matter subgalactic halos are very hard to detect. Here on the right, you have a nice picture with dwarf galaxies spanning 6 orders of magnitude in stellar masses. So from the most massive and brightest one on the top left to the less massive and faintest one at the bottom right. So for these last ones, for example, we can only detect them in a volume nearby the Milky Way. So this picture is already showing us how difficult it is to detect them using optical observations. And so this is because the dark matter halos at subgalactic scales, being smaller and being more dark matter dominated, they are extremely faint. And this is for those dark matter halos at least form galaxies, because below some 10 to the 8 solar masses, we don't even expect dark matter halos to form galaxies. Therefore, they are dark. And the only way we have to detect them is through the gravitational effect that they exert on ordinary matter, therefore using gravitational lensing. But for a dark matter halos, in order to make strong lensing on a background source, it has to be dense enough. So it has to have a density above a certain threshold. In this plot here, so in this study of Wong et al. And collaborator in 2020, they have studied in details the concentration of simulated dark matter halos. And they plotted here their concentration in function of their masses. And as you can see, basically, dark matter halos at subgalactic scales, they are far more concentrated than, for example, galaxy cluster dark matter halos. So this is telling us that from prediction, we should expect at least the cores of these dark matter halos at subgalactic scales to be dense enough in order to make strong lensing. And so because of their high concentration and small masses, these dark matter halos at subgalactic scales, we can approximate them with point mass lenses. And we know from the gravitational lensing theory that a point mass lens should split the image of a background source into 2 lensed images, whose angular separation, if the lens and the source are at cosmological distances and for order of magnitude precision, it should depend only on the mass of the lens. So if we consider a supermass, a compact object of 10 to the 6, 10 to the 9 solar masses, so I will call from now on this type of object a supermassive compact object, then we expect the angular separation between the lensed images to be in the milliarcsecond regime. And that's why we call this type of gravitational lensing system MIlli-LEnses. So as I just said, basically, the direct observable of milli-lensing are supermassive compact objects which are dense enough in order to make strong lensing on background sources. And this translates basically into this condition. So they have to have a surface mass density above a certain threshold, that is this one. And astrophysical objects that satisfy this condition can be, as I just mentioned, the cores of subgalactic dark matter halos, that they can live in the surrounding of galactic halos or free floating in the field. But there are also other astrophysical objects that can satisfy this condition, as for example, supermassive black holes at the center of galaxies, like the one in active galaxies, for example, or in the outskirts of galaxies. And also primordial black holes that, as I mentioned before, they are considered by certain model a major component of the dark matter. Until now, the search for these dark matter halos at subgalactic scales has been addressed mostly using what I will call indirect observational method. I will explain you later why I call them like that. So one of them is makes use still of gravitational lensing, but this time at galactic scales. So it means that here the lens is a galaxy with its own dark matter halos. And we can usually have this type of, these two types of scenario here. So scenario A and scenario B. In the scenario A, we have that the background source is an extended source, as it could be another galaxy, for example, or a radio loud quasar where we can resolve the jet. And in this case, we usually have the formation of arc-like structures. And in some cases, we can even have the formation of a complete Einstein rings. The case B instead is when you have the source in the background is a compact source, as it could be, for example, a quasar at optical frequencies or a radio compact quasar. And in this case, we have instead the formation of a multiple compact components. That is what we also have in the case of milli-lensing, but in this case, we are at larger angular scales because the lens is a galaxy. So usually here, angular scales are of the order of the arc-second or a couple of arc-second. So, and since in gravitational lensing, the positions as well as the magnifications of these lensed images depends on the distribution of the lens mass distributions, then basically any anomaly on these physical quantities can indicate the existence of an extra mass contributing to the gravitational potential of the lens. And this extra mass can be in the surrounding of the galaxies or in the path in between the source and the observer. Then another method is using density perturbation in the Milky Way stellar streams, where these stellar streams are basically formed by stars that are escaping disrupting globular clusters. In this case, basically, so if this stellar stream is encountering a mass condensate, as it could be a dark matter sub-galactic halos, for example, then these can introduce some perturbation in the density of this stellar stream. However, this basically the uncertainty or the difficulty in this method is that you need to know very well what are the intrinsic properties of this stellar stream in order to exclude that these density perturbations are not intrinsic instead of given by a gravitational lensing event. Then the third method still uses gravitational lensing, but this time in the time domain and using GRB, gamma ray burst. In principle, using this method, it's possible to distinguish compact objects with masses between 10 to the 2 and 10 to the 7 solar masses. And one example is this one, for example, GRB 210812A. In this paper of Ferris and collaborator 2021, they basically using the two peak of the emission and the time delay as well as the flux ratios of these two peaks, they were able to infer the mass of the lens that should produce this gravitational lensing event. So I call this method indirect observational method because in all this method, you basically, it's difficult to be 100% sure that what you are observing, so either the anomaly on this or this double peak in the GRB, is not something intrinsic more than associated to a gravitational lensing event. And so if you want instead to use a more direct method, so I mean really imaging the two lensed images at angular scales that we expect to be produced by a supermassive compact object, then you obviously need milliarcsecond resolution. And the the most direct way nowadays to reach this high resolution is using very long baseline interferometry. In this technique, antennas are, the observation are performed in conjunction by antenna located in different places around the world, and effectively using basically the entire Earth surface as if it was one unique antenna. Here I only mention the two main VLBI arrays in the Northern Hemisphere because they are the one I'm interested in. And they are the European VLBI Network with antennas located in Europe, Asia, and one in South Africa. And the Very Long Baseline Array with most of the antenna located in North America. So then we have performed a pilot search for these milli-lenses using the publicly available data in the Astrogeo VLBI FITS image database. This database contains mostly VLBI data of radio compact sources at multiple frequency and multiple epochs, because the goal of this database is to obtain a radio fundamental catalog. So at the time we performed this search, we downloaded visibility data, multi-epoch and multi-frequency for the available sources at that time that were almost 14,000 sources. We performed a stacking of the images for those sources where multiple epochs were available. And we finally create a web page based on the idea of the citizen science project to visually inspect all these images. Then we have involved 5 PhD scientists and 9 undergraduate physics students from the University of Crete in this search. And we have asked them to mark as lenses sources where multiple compact components were present in at least one of the observing band, as the example you have on the left, and instead to possibly mark as no lens sources where it was possible to clearly distinguish a jet-like structure. As a sort of a quality check, because many people were not expert in either the agent physics or gravitational lensing or either VLBI, then we have created these 200 mock lenses faking the emission of a secondary component, compact component, and placing it in any position within the field of view, as you have in this example here at the bottom. And so at the end of this first visual inspection step, we found that 8 mock lenses were missed, but fortunately 6 of them were missed by 2 persons together. So then basically we have inspected the sources that have been inspected by these 2 persons that were roughly 1,000, and we were finally then able to assess a loss rate in this first visual inspection step of 1%. Plus, we found also 4 more lens candidates, and so the number of lens candidates at the end of this first step was 954. So then we did 2 more steps of visual inspection, but this time more expert people in either the agent physics or the milli-lensing were involved. And then at the end of all this step of visual inspection, we ended up with 59 candidates. Then as a last step, we filtered sources using the surface brightness preservation criterion. So in gravitational lensing, we expect some physical quantity being preserved. And one of these quantity is the surface brightness of the different lensed image, the supposed lensed images. So, and this means that a secondary fainter component has to be smaller than the primary brightest component. And then we use this apparent surface brightness ratio between components lower than 7 to finally obtain the list of the 40 best candidates. And we published this list in this letter, recently published in Monthly Notice. So there you can find the list of these 40 best candidates. And just as a reminder, all these 40 sources have multiple compact components in at least one observing band and an apparent surface brightness ratio between components lower than 7. Then also based on spectral index information, we suggested 2 sources that have a higher probability of being a milli-lens system. And so why this basically, why the spectral index information is important. So first of all, the fact that they are similar. So as I just mentioned, so gravitational lensing is an achromatic effect and is supposed to maintain some physical quantities between the lensed images. Like, for example, the surface brightness or the flux density ratio between components, or the spectral indexes between components. Moreover, the light rays that produce the lensed images have different paths. And this introduces a time delay between the lensed images. But since this time delay depends linearly on the angular separation of the lensed images, and in milli-lenses, we are at angular separation of milliarcsecond scales, then this means that time delays in milli-lenses are very small. Usually we are talking about time delays of the order of tens of seconds or some hour, usually in any case smaller than a day. And this is important because it means that time delays in milli-lensing are not affecting either flux density ratio nor spectral index measurement. However, in the case of spectral index, we cannot exclude the fact that the 2 light rays that are crossing different plasma, they may cross plasma with different absorption coefficient, and therefore this it may lead to different spectral indexes for the 2 components, for the 2 lensed images. And so for this reason, basically, we use the spectral index only as a suggestion in this case and not as a constraint. Then the fact that they are also flat, the spectral indexes of the 2 components is also important. So here you have a famous gravitational lens system, but at galactic scale. So where in this case, the lens is a galaxy, this G1 plus another dwarf galaxy, and they are splitting then the image of a compact radio-loud quasar in the background into these 4 images. But since we know that the bulk of the emission in a compact radio-loud quasar comes from the core region, and we know that the core region has a flat spectrum, then aside from the fact of having similar spectral indexes, we also expect them to be flat, as exactly in this case, in this gravitational lens system. And this, for example, may help to distinguish between other cases where we can have a similar morphology. So we can still have a core and maybe a secondary component. This time, though, the secondary component belongs to the jet. And in this case, we expect this component having a different spectrum and also steeper, usually. But so let's say that in general, the step that we need to perform in order to confirm a milli-lens system are the following one. So we have so far we have inspected the VLBI images and we have selected the sources with multiple compact components on milliarcsecond scales. We have compared the surface, the apparent surface brightness of these components, and we have discard the one that have no similar surface, apparent surface brightnesses. And then for this first step, we only used spectral indexes as a suggestion for the two most probable milli-lens candidates. But then so now we need basically more follow-up observation, and we actually obtain a new EVN observation at 5 and 22 gigahertz that we will use basically to repeat this, and then with more information in our hand, we will also be able, for example, to use the flux ratios and spectral index with more confidence to finally obtain the most probable, this time a milli-lens candidate, that we will then use to test them with the lens modeling, to finally basically see if their flux ratios and position are in agreement with the lens model. In any case, all sources that will be finally discarded as a milli-lens system, because of their morphology, they can still investigate it as a compact symmetric object or even supermassive binary black hole candidates. So in the case of compact symmetric object, they are thought to be the young counterparts of the currently extended radio galaxies. And in this case, the emission comes from these from the hotspot at the end of these two lobes, where the plasma, the jet plasma, is interacting with the interstellar medium. And in most of the cases here, the core is obscured. And that's why this morphology resembles a lot the morphology we expected in milli-lenses system. And then here on the right, you have instead a multi-frequency VLBI observation of the only supermassive binary black hole confirmed morphologically. And this is interesting because we would expect to see many more if we are based on the hierarchical merging theory and the fact that most of the galaxies have a supermassive black hole at their center. So as I mentioned before, we have asked and obtained EVN time for the follow-up of our 40 milli-lens candidate that have been performed with observation at 5 and 22 gigahertz in phase referencing for a total of 140 hours, split in 5 observing sessions. Since the analysis of this data is still undergoing, I will just show you some example. So one interesting source is this one, 0527 plus 1743. In our new EVN 5 gigahertz observation, it confirms this double compact feature structure. And we are also able in our new observation to discard the third component that we were observing in the Astrogeo image as a probable artifact. The two components still respect the surface brightness criterion. But when we measure, for example, the flux ratios of the two components at the closest frequency, we see some discrepancies. So then this means that most probably this is not a milli-lens system, but obviously we will need more analysis and also the 22 gigahertz information to confirm this. Another interesting source is this one, J0237. This source is showing a different morphology in our new EVN 5 gigahertz observation. And we think that here what plays a role is the variability of this source. So probably in the Astrogeo epoch, it was ejecting a secondary component, while in this new observation, it just shows a more simple core jet-like structure. And in support of this scenario is also the position, the astrometric position of the optical emission as given by Gaia, that is closer to the core and not in between the two compact components, as we would expect if this was a gravitational lens system. Then the last one is this, so J1143 plus 1834. This source is interesting because we were able also to recover the 22 gigahertz emission from both compact features. I'm afraid I cannot tell you more because the analysis is still undergoing. But in any case, even if we will discard this source as a milli-lens system, it's still a very interesting, this one is still a very interesting source that was associated, was classified as a CSO candidate or even a supermassive black hole, a binary black hole candidate in previous studies. So what I presented to you so far is was a pilot project for a more extended project, the SMILE project, a more extended that we plan to perform using the VLBI data of roughly 5,000 radio loud sources. More extended in the sense that in this case we will take care of data from scratch, so also from the calibration. A radio astronomer know how this is a very time-consuming task. And so now I will tell you basically the idea. So the idea behind this project comes from these two pioneering studies. So Press and Gunn in 1973 first developed the idea that the number of gravitational lensing events by supermassive compact objects directly probes the mass density, therefore the abundance of supermassive compact objects in the universe. And then later on, Wilkinson et al. In 2001 used this idea to constrain this abundance for supermassive compact objects with masses between 10 to the 6 and 10 to the 8 solar masses, using a smaller sample than what we plan to do in our SMILE project. So using a sample of 300 sources and VLBI data. And this is the constraint here, this one, that they obtain with no milli-lens found. With our project, instead, we plan to constrain the abundance of supermassive compact objects with masses between 10 to the 6 and 10 to the 9 solar masses with more than an order of magnitude better precision than in Wilkinson et al. 2001. In this plot here, you have the density of the universe locked up in an object of a certain mass versus that mass. And as you can see, the constraint we will obtain with our project will be below the LambdaCydia prediction, while this was not the case for the constraint in Wilkinson et al. 2001. So then basically our goal, as I just said, is to constrain the abundance of supermassive compact objects in the universe with roughly 16 times better precision than in previous studies. And in order to do that, then we have to move to a sample that is roughly 16 times larger than in previous studies. So therefore, we have collected a sample of almost 5,000 sources using the original catalog from the class survey, being a class the most successful to date search for gravitational lens system on galactic scales and using radio frequency. So we have then used basically the class catalog, and then we have selected the sources with a flux density at 8 gigahertz higher than 50 millijansky. And in this way, we ended up with a complete sample of 5,000 sources. So then we have cross-match this because we want to have a new VLBI data or to have VLBI data of these sources. And so we cross-match this list with the archive, and we find that 75% of the data, of our data, of the data for this project are already collected in the archive. So then we proposed for data for the remaining sources, and we obtain observation. So the 25% of data instead from the SMILE sample comes from newly obtained observation. So since we are interested in, so the direct observable of our SMILE project will be the abundance of this supermassive compact object. But since we are interested in a particular type of supermassive compact object that are these dark matter halos, the sub-galactic scales, then what we want really to know is what is the number of these dark matter halos that we are able to detect through milli-lensing. And this depends on on how dense, as I said at the beginning, are these dark matter halos, and on the mass function of these dark matter halos. And both these quantities are obviously set by dark matter particle properties. Then this number also depends obviously on the experiment, mostly on the size of the sample. And SMILE will have the largest sample ever for this type of search. So then, in order to compute this number, we have used the optical depth of each source in our sample. We have computed this optical depth, where this optical depth is basically the probability that a source has to be lensed by an object along its path, so in between the source and the observer. And this optical depth, this quantity depends on the redshift of the source. And we have information, redshift information for 2/3 of the sources in the SMILE sample. For the remaining one third, instead we assume a similar redshift distribution. It also depends on the number density of the supposed lens population, that in this case are our dark matter halos, and this, as I just said, then this parameter here will depend on the density profile and the mass function. So then this quantity here is the one that is different for different dark matter models. Then this quantity also depends on the lensing cross section, that in turn depends on the length of the mass of the lens and the redshift of the lens and the source. And then finally, it also depends on the lens path that in turn depends on the cosmology used and the redshift of the source. So basically then, once we have computed this optical depth for each one of the sources in our sample, then we just have to sum over all the sources, and we will obtain, we have obtained the number of expected dark matter halos that we will detect through milli-lensing with our SMILE project. And this is exactly what I show you here. So we have computed this number for different dark matter models. So here you have the number we expect in the case of warm dark matter, or the warm dark matter model, this one here, that is 0 because of the cutoff that I show you at the beginning. Then we have computed this number for 3 different cold dark matter models that have different density profiles. So in 2 of them, the density profiles comes from theoretical prediction and simulation. In particular, we have this one that is the Navarro-Franken-White density profile, and in this one is the density profile associated to core collapse or self-interacting dark matter model. And then the third model instead, for the third model, we have used density profiles derived from observations of galaxy cluster. And the important thing here is that, as you can see, different dark matter models will give us a very different number of expected dark matter halos that we can detect through milli-lensing in our SMILE sample. And so this basically means that SMILE will allow us to robustly discard some dark matter models. While this, for example, was not the case in previous studies, just because of the size of the sample. In fact, so considering that the 2 samples in our project SMILE and in Wilkinson et al. 2001 have a similar redshift distribution, then we can use basically this formula here to infer exactly this number for the different dark matter models in the case of the study of Wilkinson et al. And that we can compute using this the number in SMILE and this factor here. And so basically this gives us 0 for all the dark matter models, so less than 1. So it means that Wilkinson, because of the sample size, the constraint in Wilkinson et al. 2001 was not able to distinguish between these different dark matter models. So and here I reach my summary. So just as to remind you what I've been presenting. So we presented the pilot search for gravitational lenses with angular scale, with milliarcsecond angular separation And for this, we use VLBI data in the of almost 14,000 sources from the publicly available catalog in the Astrogeo VLBI FITS image database. The direct observable of MIlli-lensing are supermassive compact objects, such as dark matter sub-galactic halos, or even primordial black holes, or supermassive black hole that we can find in the center of galaxies. So then we found in this pilot search 40 milli-lens candidates that have multiple compact components in at least one observing band and an apparent surface brightness ratio between components lower than 7. So then we followed up the 40 candidates with EVN, new EVN observation at 5 and 22 gigahertz, and the data are still under analysis. So I've just presented you some preliminary data, some example. And so sources that will be finally discarded as gravitational lens system can be still investigated as a compact symmetric object or even a supermassive binary black holes. And then finally, we are planning, if we are currently looking for funding, so if funding, we are planning to extend this project and to perform a similar search on a complete sample of almost 5,000 radio loud sources to obtain a new constraint on the abundance of supermassive compact objects with masses between 10 to the 6 and 10 to the 9 solar masses. And we will obtain a constraint that is more than an order of magnitude with more than an order of magnitude better precision than in previous studies. And this will allow us to discard some currently viable dark matter models. So thanks.
Thank you very much, Carolina, for this talk. And now the talk is so open for questions. Please, if you want to do a question to Carolina, raise your hand, your electronic hand, and I will let you open your micro. So questions. Okay, Rainer, please, go on.
Not really any big questions. It was fantastic. I just want to say that I'm very impressed. I really like your talk, Carolina. Very, very good work. Very clearly presented. The only thing, I think maybe this concentration parameter at the very beginning, the second or third slide, I didn't understand what it was and why the smaller ones are more concentrated than the larger ones. Yeah, this one. This one. I didn't understand this graphic.
These are results from so it's from a simulated dark matter halos. So they have computed this. So the concentration is a parameter for the density of these dark matter halos, and yeah, and they have, so then they have computed this concentration for different dark matter halos masses.
But what are the X and the Y axis? So, I mean, the larger the number, the more concentrated, I guess, on the Y axis. And what is the X axis?
Yes, the masses. So this M200 is usually 200, the virial, so it's considered virial mass. Yes, in unit of solar masses. So 10 to the 15 is usually the virial mass for a galaxy cluster dark matter halos. We are around that values. And then if we talk about sub-galactic dark matter halos, we are something like in this orange and line below. So something.
Okay, thanks. Thank you.
Rainer, Jose Diego, have a question, please. Go
on. Thank you, Carolina. Really nice talk. So you mentioned earlier that the surface brightness is used to discriminate between good and bad candidates. But most of the images you showed, your images are unresolved. And in this case, how do you factor in the fact that you have some kind of PSF convolving your image?
Yeah, the surface brightness, the value that I compute are not from the image plane, but I usually model fit the visibility data. And then from the model fit component, so doing like that, you shouldn't be affected, for example, by the beam. Then from the model fit component, I extract basically the size of the emitting component and the fluxes, and I compute it I computed the surface brightness then value.
Okay, thanks.
Thank you. More questions, Carolina? Okay, I do not see any more questions, so maybe we can close the talk. Thank you very much for this wonderful talk, and see you in the next seminar. The talk will be uploaded to our communication channel, so you can follow on this subject there. Thank you very much, Carolina.
Thanks. Thanks to all of you.
So I stop recording now, Carolina.